So good day guys, welcome to our second workshop. So in this workshop, I'm gonna go over the continuity questions on this worksheet. And if time permits, I will also go back to do some limits questions for you. So let's get started. The first question here, using the graph below, determine if f of x is continuous at these places, x equal to 2, x equal to 0, and x equal to 3. So firstly, we need to be sure what the definition is for f of x to be continuous at some point. For example, for this point, I'm going to write out the definition. F of x is continuous at x equal to 2. The definition is limit x from the left side of -2, that is -2 minus, right? It's equal to limit x from the right, that's -2 plus f of x. It's also equal to f of -2. That's the value of the function evaluated at the point x equal to -2. So that is the definition theoretically. But now we're given a graph, so we want to check the definition by using this graph. How can we do it? First step is gonna choose the point on the x-axis, that is x equal to -2. This is my blue point. Now we're gonna check the left limit when x approaches -2 from the left side. So we're gonna choose a point on the left side of this blue point on the x-axis, just a little bit to the left, maybe here, okay? And I'm also gonna look up to my graph to find the corresponding point on the graph. And after that, I'm gonna drag this blue point on the x-axis, the green point on the x-axis to approach the blue point. So this green point is gonna go here, okay? And you can imagine the blue point, the green point on my curve is also moving accordingly. So when this is moving towards the blue point, suppose maybe it's here, right? Then the green point on my curve is gonna move accordingly to here. And you can imagine that this picture where my at the moment my green point is kind of nearly touching the blue point. Then where is that green point goes on the curve? It's gonna go here, right? All the way to this solid point here. I will denote that by the orange point. Right? So this process is how the x is approaching -2. But what we want to focus is how the value of the function changes. So in this process, we are gonna take a look at the y value of the green point on the curve. That is the function value evaluated at the s points accordingly. And you can see that the y value of the green points on the curve is gonna approach the y value of the orange point. So you can see that where my x approaches -2 from the left side of -2, then the value of the function is gonna approach the y value of the orange point, which is 2. right? So I have my first left limit here from the curve, that is 2, okay? So the left limit is equal to 2. So we also, now we finished the left limit, and now we want to go to the right limit and the value of the function to check all of them. So I'm gonna put a question mark here since we haven't checked this, right? So put a question mark here. That means these two equal signs, they have to be checked. Okay, so now that is the left limit equal to 2. Now let's go to the right limit. For the right limit, I'm gonna choose a point on the x-axis on the right side of the blue point. Maybe here, denoted by the green point. And I'm gonna look up to my curve, which is here, right, to find the corresponding green point. And what I want to do is to drag this blue point on the x-axis toward the point x equal to -2, the blue point. And you can imagine the green point on the curve is gonna also move accordingly. So at the moment, the green point is kind of nearly touching the blue point. My green point on the curve is gonna move toward this direction, and it's gonna touch this open circle. I will denote this by the also this orange point, maybe another color. Well, I will choose maybe this pink. Okay, this pink point here. This pink point here. I don't want to fill it because you know, it's an open point, and then because I'm also going to use this information later. Okay, so this is my pink point here. So you can see that the now the green point on the curve is gonna approach the pink point. So its y value will be approaching this y value of the pink point also. Okay, so the value of the function is gonna approach -1, right? -1 here. That means my right limit, it's -1, right? That is when x is getting closer and closer to the blue point from the right, -2, then the value of the function is gonna be getting closer and closer to the value, the y value of the pink point, that is -1. Okay, so I have checked this, left limit and right limit. Now I also need to check the value of the function evaluated at the point -2. So that is my my orange point, because the orange point was originally solid. If you remove it, you see that dot was solid. Right? So when it's solid, that means the value of the function is at there. So I have now my f of -2 equal to 2. So from this example, I have demonstrated how we can find left limit and right limit, and also the value of the function by using the graph, right? And after we found them, we can easily check whether they are the same. If they are the same, then f of x is continuous at this place. Otherwise, it's not. And we can see that these three things are, there are only two of them are equal, right? Left limit is not equal to the right limit. And therefore, f of x, it's not continuous at the point x equal to -2 by the definition. So I will put a cross here, meaning that f of x is not continuous at this place. Okay, so that is how we start. And now let's move on to the next place, that is x equal to 0. We're gonna do the same trick. Okay, find the x point, x equal to 0 on the x-axis, and then choose a point from the left. Okay, and then look up to your graph, find the corresponding point, and then drag this point along the x-axis. So the green point on the curve is gonna also move accordingly. And you see that at the moment the green point is touching the blue point, then the green point on the curve is gonna touching this kind of the point 0, 1, the solid dot on the curve there. So now we can conclude from the curve that from the graph that limit x goes to 0 from the left side, f of x, the limit from the left is equal to 1. Okay, and now we do the right limit. Choose a point from the right, look up to your graph, find the corresponding point, and then drag this point along the curve, right, so that the point on the curve is going to move accordingly, and see where it goes. It goes toward that same solid dot, which is also 0, 1. So now we see that when x approaches 0 from the right side, the value of the function is also approaching same value 1. So we have the left limit now equal to the right limit. The last thing we have to check is the value of the function, right? The value of the function, just need to look up to your graph. From this blue point, you see that you have this solid dot here, right? So that is the value of the function, which is also equal to 1. So these three things are equal. By our definition, f of x, it's continuous at a place x equal to 0. So I'll put a check mark here, meaning that f of x is continuous at this place. So you see that same method, we go through these three things to find left limit, right limit, value of the function, and check whether they are the same. It's kind of straightforward. Now let's do the third one. Okay, third one. So x equal to 3. So I'm gonna find a point x equal to 3 on the x-axis, which is here. And I don't want to fill this, so pretend that my blue point is overlapping the open circle here. Okay, and now I choose a point on the left side of this blue point. Look up to your graph, right? Find the corresponding point, and then drag this point along the x-axis and see where that corresponding point is going. It's going toward this the open circle there. So from this, we see that the left limit (3 minus f of x) it's equal to 0. Why is it 0? Because the y value of that open circle is 0. That is the y coordinate. Okay, and do the same thing for the right limit. Choose a point on the x-axis, look up to your graph, find the corresponding point, and then drag this point along the x-axis and see where that corresponding point is going. It's going toward this open dot there. Okay, and so the right limit, by the definition, is also 0, right? It's going to the same place. Okay, so we have already had left limit equal to the right limit, both are 0. Now we're gonna find the value of the function, right? So we're gonna go from the point x equal to 3 on the x-axis, which is here, right? And then look up to your graph, and you find that the value of the function is here at this solid dot, which is, below the x-axis. So now we have the y value of this solid dot here, that is -1, right? So the value of the function evaluated at x equal to 3, it's -1. Now you see that even though the left limit is equal to the right limit, however, they're not equal to the value of the function. And therefore, by our definition, these 3's are not equal to the same value. So f of x, it's not continuous at x equal to 3. Okay, I think it should be very clear right now how to use the graph to find out whether f of x is continuous. Okay, so that is our question 1, how to use the graph to do things. So we're gonna move on to the question 2. It's the same type of question, but this time we're not gonna use the graph, and instead we're gonna remember the definition and just solely check the definition by using the formula of the function. Okay, let me get some space here. Question 2. Okay. Find the values of k for which the function is continuous. What does it mean by the function to be continuous? Function f of x is continuous if and only if the function is continuous at each single point of its domain, right? So the domain of this function, we're gonna first take a look at this domain. It's obviously all the real numbers, because the domain is all the valid input. You can input every number in this expression. You also always get a defined output. So the domain is all the real numbers, and we see that this is a piecewise function, right? So on each of its pieces is gonna be continuous automatically according to the expression. These two expressions, they're both elementary functions. By saying elementary functions, I mean basically all the functions we have encountered, rational functions, the trig functions, right? The polynomial functions, all these functions we have encountered, we give them a name. Those are called elementary functions. So these functions, they're all continuous within their domain. Okay, so it means that the only potential places, right, where f of x may be continuous is at those breakpoints. Is where those pieces are joined together. And now we see that the breakpoint here, it's x equal to 1, right? So breakpoint, the only breakpoint is x equal to 1. So to check whether the function is continuous, we only need to check the continuity of the function at x equal to 1. That is, the nature of this question. We have, turn the continuity of this function into just continuity of this function at one single point. Now we're gonna check continuity of f of x on this point. And by our definition, f of x is continuous at x equal to 1. It's equivalent to left limit 1 minus equal to limit x go to 1 from the right, f of x equal to the value of the function f1. Okay, so it's basically the same as the previous question. We're gonna check these three things and see that if they're equal. Okay, now go from the left limit. Now you have your x-axis here, and this is your point, x equal to 1, right? And then you're gonna choose a point from the left. This is your x, and this point is gonna approach this 1 from the left side, right? So you see that when you choose this point from the left side, the x is less than 1. Okay, when x is less than 1, how can we evaluate the value of the function? Well, according to the formula, when x is less than 1, you need to choose this expression. Okay, 7x minus 2. So we're going to write limit x approaches 1 on the left side, f of x is equal to this 7x minus 2. Then we can evaluate this limit, just plug in, that is 7 minus 2, which is 5. Okay, so left limit now is equal to 5. And now we're gonna check the right limit, so choose a point from the right side, this orange x, and this point is gonna approach 1 from the right side. So you can see that on this x-axis, the orange x is greater than 1, right? When x is greater than 1, how can we evaluate the function? From the expression here, you see that we have to choose this expression, kx squared. Okay, so I'm gonna write this. X approaches 1 from the right, f of x. It's equal to, now choose the orange expression, that is kx squared, right? And now we're gonna plug in, so it's gonna equal to k. So left limit is 5, right limit is k. And now let's find the last thing, that is the value of the function f of 1. Okay, f of 1, when x is equal to 1, you're also going to use the green expression because there is an equal sign there in the green expression. So you're going to substitute 1 into the green expression to get your value of the function. That is 7 minus 2, which is 5. Now we have these three things here, right? And then since the function is continuous, it has to be continuous at the point x equal to 1. And these three things, they have to be equal. So this is my 5, right? This is my k, this is my 5, right? Since they have to be equal, it forces this unknown k to be equal to 5. Okay, so now we have find the value of k for the function to be continuous. It has to be equal to 5. If k is not 5, then the function is gonna be discontinuous at the point x equal to 1, and therefore it will be discontinuous as a function. Okay, so that is our question 2. We're using the exact same stuff to do the question, but this time we're not using the graph. We just use some abstract expression here, and then evaluate the limits by plugging in the value. Okay, so I hope that you see the common points of these two questions. That is our question 2. Now let's work on the next one, that is question 3. And I will go a little bit faster since we are familiar with the definitions already from question 2. Determine the values of a and b that will make the function continuous. So basically the same trick. You're gonna see what the breakpoint is for this piecewise function. And for the function to be continuous, we only need to check the continuity for the breakpoints. So find out the breakpoints. Okay. First, maybe domain. It's all the real numbers, as usual. You can plug in whatever values according to the range of x. And the breakpoint, the only breakpoint here is x equal to 1. So we're gonna check the continuity at x equal to 1, and then write out the definition. F of x, it's continuous at x equal to 1. It is equivalent to the left limit equal to the right limit is also equal to the value of the function f1. So we're gonna check these 3 things, okay? To give you a better picture, I'm gonna draw this, right? This is my breakpoint 1 here. And take a look at the limit from the left. This is the x point, right? Approaches this from the left side. So you see that the green x is less than 1. Okay, green x is less than 1, which means when evaluating the function, I'm gonna choose this expression. Okay, the green expression. So limit x goes to 1 on the left side. F of x is gonna be limit x goes to 1, this 2x squared plus 3ax plus b, right? And I can plug in 1 into x, so I have 2 times 1 squared times plus 3a1 plus b, which is, 3a plus b plus 2. Maybe write it here. That is equal to 3a plus b plus 2. And now I'm gonna choose another point that is on the right of 1, this orange x, and this point is gonna approach x from the right side. So you can see that the orange x is greater than 1, right? Orange x greater than 1. Green x less than 1. So since orange x is greater than 1, I'm gonna choose this expression as my orange expression when x is greater than 1. And now I find the limit on the right according to this discussion. Limit x goes to 1 from the right side is gonna be this thing. And now I plug in, right, 2b plus a. Okay, that is my right limit in terms of a and b. And we know the last step is to find the value of the function. So the value of the function evaluated at 1 is going to be 9 here by the definition, right? It's going to be 9 here. So I have now f1 that is equal to 9. Now we have these three things here. They have to be equal. The left limit has to be equal to the right limit, has to be equal to the value of the function. Okay, so now we have these three things equal together. 3a plus b plus 2 equal to the 2b plus a equal to 9. Okay, now I can 2b plus a. Solve this thing by eliminating the maybe the b, right, and substitute that into the previous the other expression. So by solving this, I can have, you know, a equal to 9 minus 2b, right? And I can plug in my 9 minus 2b into this expression. So I have now a is equal to 9 minus 2b, so 3 times 9 minus 2b by substitution plus b plus 2, right, is equal to 9. Because this 3a plus, you know, b plus 2 is also equal to 9. Okay, so I'm gonna solve this. That gives me 27 minus 6b plus b plus 2 equal to 9. So I have this negative 5b, right? This plus 29 equal to 9, right? So negative 5b it's equal to negative 20. So b is equal to 4 if we divide both sides by 5. So b is equal to 4, and now we can plug in b equal to 4 into the previous expression. And now I have 2 times 4 plus a equal to 9, right? Which gives me that a plus a is 9. So a is equal to 1. Okay? So now my answer is a equal to 1, b equal to 4. So this solution, the value of a and b, will make the function continuous at 1. Okay, by the discussion above. So basically, question 3 and question 2 are exactly the same. Use the same trick to find left limit, right limit, the value of the function, to kind of establish some kind of algebraic equations. And by solving the algebraic equations, you find the value of that unknown, right? And in question 2, the algebraic equation we establish is quite simple. It's just k equal to 5. We don't have to solve it. But in question 3, the algebraic equations we establish, it's a system of two linear equations, which we, it takes a little bit time to solve it. A equal to 1, b equal to 4, but idea, it's exactly the same. Okay, so just more computation, nothing else more different. So that is our question 3. a equal to 1, b equal to 4. Now, let's move on to our question 4, which may be challenging, but we're ready for it. So take a look at this question. Find the values of x where the function is continuous. Is the function continuous at x equal to 0? So there are two questions here. Find the value of x where the function is discontinuous. Okay, so there's no parameter here. So how can we find those places where the function is discontinuous? As before, this is a piecewise function. So for the piecewise function, the only places, right, potential places where the function could be discontinuous is those breakpoints. So we're gonna find out the breakpoint first, okay? There are two breakpoints here, that is -1 and 1. So these are the only, potential places where the function could be continuous. So we're gonna be checking the continuity for the function solely on these two places. So what we do now is to check the limit, left limit, right limit, and value of the function for these two places respectively. So for the x equal to -1, we have left limit x goes from this left, right, f of x. And to be clear, let me draw my lumber line so that you can see how to find left limit. So this is my -1, right? Left limit, you're gonna choose a point from the left, this x here, and this approaches -1. So you see that the green x is less than -1. Less than -1, you're gonna choose this expression, okay? So this one here, it's gonna be limit x goes to -1 minus x squared, okay? And now plug in, it becomes -1 squared, which is 1. So that is just the left limit. Now check the right limit. You choose a point from the right. This x, orange x, approaches this point. So the orange x is greater than -1. When it's greater than -1, you're gonna choose this expression, right? See that? X is between -1 and 1, right? You're gonna choose this expression. So limit x goes from -1 plus f of x is going to be limit x goes to -1 plus x, right? And you plug in, you get -1. Okay, so so the left limit is already not equal to the right limit, so we can just conclude from here that the function f of x is discontinuous at the place x equal to -1. But for completeness, let me also find the value of the function for u, f -1, right? That is equal to -1 by the orange expression, because there is an equal sign here, which means when x is equal to -1, you also choose the orange expression. Okay, so we can conclude that now these three things are different. So f of x is this continuous at x equal to -1. Okay. Now we're gonna move on to the next point. That is for x equal to 1, the other breakpoint. We check limit x goes to 1 from the left, right? And as usual, draw my number line just to be clear. This is x, right? From the left, you're gonna choose this, maybe another color, while running out of colors. So maybe red, okay, red x here. So red x is less than 1, right? Less than 1, you're gonna choose this expression, right? When it's less than 1, so the orange expression is actually the same as the red expression from the formula. X is less than 1, you choose that expression. So this is gonna be equal to limit x approaches 1 minus x, plug in, and you have 1. That is the left limit. For the right limit, do the same thing. Right. Now choose a point, maybe this time the gray point here, gray x, right, is greater than 1. Greater than 1, you're gonna choose this gray expression, this one here, 1 over x. Okay, 1 over x plug in 1. Okay. Now the value of the function f1. f1, there is an equal sign here for the x equal to 1. So you're gonna choose this expression as well when x is exactly equal to 1. So plug in 1 here. That is 1 over 1, which is 1. Now you see that the left limit is equal to the right limit, which is also equal to the value of the function. They're all 1. So we conclude now f of x, it's continuous at x equal to 1. Okay, so that is by the definition. Now go back to the question itself. We want to find the value of x where the function is discontinuous. So the only point the function is discontinuous, it's x equal to -1. For the other points, the function is continuous. So it seems that we have answered the question completely. But the question also asks, is the function continuous at x equal to 0? So technically, we can ignore this, right? Because as I said, for piecewise function, the only places where the function could be discontinuous is those breakpoints. So we have checked all the breakpoints, and 0 is not a breakpoint, and therefore the function is continuous. But some of you may be confused here. Did we actually, ignore to check the domain, right? It's 0 actually inside the domain of this f of x. Somebody may doubt that, right? And somebody may, concerned about the expression here, 1 over x, right? we know that denominator cannot be 0. So the question, maybe the potential confusion for us right now is whether the point x equals 0 is inside our domain, right? If it's inside our domain, by our previous discussion, the function will be continuous because this is not one of the breakpoints, right? If it's not inside the domain, we may be concerned about it. So let's talk about the domain right now. Okay. What is the domain? Domain is all valid input. Can you input 0 into this function? When x is equal to 0, you're gonna, use this expression. Because 0 is in between 1 and -1, right? So f0, it's 0 in this case, right? Why is not like 1 over 0? Because, this expression, this gray expression, it's only valid for those x's greater than or equal to 1. If x itself is not greater than or equal to 1, we don't use this expression at all, right? So for x equal to 0, we're not going to even look at this gray expression. We're not going to plug into gray expression. We plug into the gray expression only when x is greater than or equal to 1. So this 1 over x, this expression is always valid because it is, already assumed that x, the input, is already greater than or equal to 1. It will never be 0. So that is the point that we should, take a look at. So by my discussion, 0 is a valid input, right? So 0 is inside the domain, right? So the domain includes 0, right? It's all the real numbers. Why it's all the real numbers? Because for whatever real numbers, you can always get a valid output. For whatever value, according to that value, which range that value is in, according to that, we can always find a valid output by the formula. So this question is kind of obvious, right? 0 is continuous. I should say f of x is continuous at 0. It's just a trap to see whether you actually understand the definition of domain and continuity and definition of piecewise function. So yes for this question, okay? The only places where the function is not discontinuous is it's x equal to -1. So that is our question 4, a very great question here. Now let's take a look at the next question, question 5 here. It's a question about the intermediate value theorem. So use the intermediate value theorem to show that the function f of x equal to x to the 4 minus 4x plus 2 has a root between 0 and 1. So let's just recall the steps, how to use intermediate value theorems. So the first step is to choose an interval denoted by here a, b, right? And then you also need to make sure f of x is continuous on the interval you've chosen, right? And the third step is to show that fa times fb is less than 0. So basically that is fa greater than 0, fb less than 0, or fa less than 0, fb greater than 0. So the sign of fa and fb are gonna be different. So the product is less than 0. That is what I mean here. So basically you're showing that f of x evaluated at the endpoints of these of this interval is gonna be different. Okay, so that is fa times fb less than 0. And the last step is conclude from the intermediate value theorem that fx equal to 0 has a root between a and b, or has a root inside this interval from a to b. Okay, so that is the 4 steps we must follow to use the intermediate value theorem. So now let's do it. Choose an interval. Sometimes the interval is given, sometimes you need to find that interval yourself. In this case, that interval should be 0, 1. Let's try that. If that doesn't work, we will choose another interval. Okay? And make sure the function is continuous on this interval. Is that true? That is true because f of x is a polynomial function which is continuous everywhere, right? Like I mentioned, it's a elementary function, right? So we have f of x equal to x to the 4 plus minus 4x plus 2. It's continuous on 0, 1. You must mention this because that is the very first assumption of the using the intermediate value theorem. Without this, you're gonna be taking some points off. So you must mention this before you use the intermediate value theorem. So that is the very first assumption. So this theorem applies. Okay, and now we're gonna check the function evaluated at the endpoints. So f0, it's equal to 0 to the 4 minus 4 times 0 plus 2, which is positive 2, right? Greater than 0, right? We have the sign, positive sign for this value. And evaluate at the other endpoint, f1, I have this 4 times 1 plus 2, which is 1 minus 4 plus 2, that is negative 1, less than 0. So f of x evaluated at the endpoints would have different signs. Okay, so that is our third step, right? Show that fa times fb less than 0. Right? So f0 times f1 is less than 0. Now we can conclude by the intermediate value theorem. So by there is some c inside this interval, okay, 0, 1, so that fc is equal to 0. That is, somebody may ask, why is that the root? Well, because f of c equal to 0, meaning that c to the 4 minus 4c plus 2 is equal to 0, right? Meaning that c is a root of the equation x to the 4 minus 4x plus 2 equals 0, right? And we know that c is in between this 0 and 1. So that is how the solution or the root of the equation is related to the intermediate value theorem. And the way we construct the equation is just let f of x equal to 0. Okay, so that is how we use the intermediate value theorem. Just remember to follow these 4 steps, right? Make sure to state that first f of x is continuous on that interval you've chosen, so the intermediate value theorem applies. Otherwise, you're gonna be taking some marks off if you ignore kind of neglect to mention that, because that is the very first assumption. Otherwise, we cannot use this theorem. So that is our question 5, not super technical. The proof is always constructive. Now let's take a look at the next question and see how different it could be. So use the intermediate value theorem, right, to show that there exists a solution to the equation, right, cos of something equal to 1 over x. You need not to find the solution. So there exists a solution doesn't mean that we know what the solution is. So just follow the previous steps, okay? We have to firstly choose an interval, right? And that interval now is not given, so you need to find that interval yourself, okay? And also make sure the function is continuous on that interval, and also the function is not given. You have to create the function yourself, create the interval yourself. So that's why I said this is kind of a constructive proof type of question. So now we're gonna choose the function first, right? I'm gonna choose f of x simply just by moving the other one to the other side. So move this to the other side. That is cos of x minus 1 over x. Why is that? Because this equation, it is equivalent to this equation, cos pi x minus 1 over x equal to 0, right? By moving this to the other side. So I have to create some function so that the function equal to 0 gives me the exact same equation. So now I let f of x equal to this guy, right? And then by letting f of x equal to 0, I will have the same, equation. And later on, I'm gonna choose the interval a and b and show that the sign of the function evaluated at the endpoints are different to apply the intermediate value theorem. So firstly, constructing the function is very important. You should know how to construct this function. Is just rewrite the given equation, right, in this form, moving everything in on one side, right, and then let that function to be that expression. Okay, so I'm gonna create my function here, right? This is my function. So this function, of course, I create this function, so I have to know what the domain of this function is, right? The domain of this function is everything but not 0, right? X is not equal to 0. You can plug in everything except for 0. So why is that important? Because you're gonna later on create your interval. Because we know 0 is not in our domain, so your interval should not include 0. if your interval includes 0, since f of x is not defined, on that point, so f of x is not gonna be continuous on that interval. That is the second step we have to make sure. So you can choose a interval that contains 0, because that will make the assumption false. Right? You can apply the theorem. So this is a very important point to notice when you construct your function. You need to notice the domain. Now I know that as long as x is not 0, the function is continuous. Right? It's a elementary function. Right? It's the trig function minus the reciprocal function or rational function. Right? So we know that f of x is continuous whenever x is not equal to 0. Now, how can I choose the interval? So I will need to choose 2 points where the function evaluated at these points have different sign. So I'm gonna try, maybe try f of 1 first. Right? F of 1 is equal to cos pi times 1 minus 1 over 1. We know cos pi is -1. If you're not familiar with this, look up the table value. I'm not gonna go over here. So cos pi is -1 minus 1, that is -2. Okay, negative sign, which means that the second point I choose should have a positive sign evaluated by the function. So maybe choose 2, right? Choose 2 cos 2 pi 1 over 2. So cos 2 pi is 1, right? 1 minus 1 over 2. Wow, that is fantastic. It's a positive sign. So later on, I can choose the interval, right? 1, 2. And then apply the, intermediate value theorem. So f1 times f2 is less than 0. Right? But I don't know that. I don't know I should choose the interval 1, 2 before I try this out. So that's why I said this is a constructive proof. So I'm gonna fill out the gap here, right? This function I've just created, it's continuous on this interval 1, 2, right? I don't know I should choose 1, 2 before I try this out. Okay, so I fill out this gap, and then because we have this f1 times f2 equal to less than 0. So by IVT, there is some C in between this 1, 2, such that f of C equals 0, right? And that being said, cos of C times pi times C minus 1 over C is equal to 0, right? And it means that C is a solution of the equation cos pi x equal to 1 over x. Okay, right? So we have successfully find a number C in between 1 and 2, such that C is a solution of this equation. That is the requirement of the question. And then we also, follow these 4 steps to use the intermediate value theorem. we've chosen an interval that is 1, 2, right? Even though we didn't know this before we tried out these 2 points. And we also make sure the function is continuous, right? By the discussion, right? Elementary function, right? And also this interval does not contain the 0, as I said. And then I've also shown that function evaluated at these 2 points have different sign. This is less than 0, so I can apply the intermediate value theorem. Okay, so that is our question 6, very constructive. And somebody may be wondering, can I choose some other points instead of 1, 2? Absolutely, you could. Yeah, you could choose some other points. For example, I choose 1 and 4. Would that work? That will work, right? So if you don't choose 2 here, you can choose 4, right? What is F4? F4 here, it's maybe, well, write it somewhere else. So F4, it's cos pi times 4 minus 1 over 4, right? Which is also 1 minus 1 over 4. That is 3 over 4 greater than 0, right? Cos 4 pi is the same as cos 2 pi. So this interval is not necessarily to be 1, 2. It could be 1, 4. So the constructive interval is, not unique, That is, up to you. As long as your interval is valid, right? The function is continuous on the interval, then you can use that interval. So different people may have different answer for this question. And that is how you know which interval you should choose, by testing the function evaluated at the endpoints. So that is our question 6, okay, by using the intermediate value theorem. So we may not have enough time, so I will just go over question 25 from the limit sections there. So this is a very common question for exams, especially when this x approaches negative infinity. We know that for this type of limit, the trick is to divide the top and the bottom by the highest power in the denominator. So what does that mean? Maybe let me just briefly mention that. So from question 23 to 26, they're all of the same type. We always divide the top and the bottom by the highest power in the denominator. For example, question 23, you're going to divide the top and the bottom by x squared, because x squared is the highest power, right? And for question 24, you're going to divide the top and the bottom by x to the 3, because this is the highest power. For 25, you're going to divide the top and the bottom by x, because x is the greatest power. Okay, so for the question 26, you're going to divide the top and the bottom by x to the 3, because x to the 6 is the greatest power. However, x to the 6 is inside the square root, so this is equal to x to the 3. Okay, so that is the trick. And what we need to pay attention to is when we have x goes to negative infinity. Now see what we need to pay attention to. We divide the top and the bottom by the highest power in the denominator. In this case is x, right? So we have now the top can be written as 1 over x times square root 2x squared minus 5x plus 3, because dividing by x is the same as multiplying 1 over x. And the bottom has been converted to 1 minus 7 over x. So the difficult point it's how can we put this thing into the square root. So we know that when we want to put something in the, or move this thing into the square root, we have to make sure that this thing is positive. So I will give you an example here. For example, you have 2 square root of 2. You can move this 2 inside the square root by squaring it. So this becomes 2 squared times 2, which is 8. However, when you have a negative number, you can't do that, right? This is not equal to negative 2 squared times 2 square root, because the left side is negative, the right side is positive. And instead, you can only let the positive part go into the square root, with the negative sign left outside of the square root. So this can only be written as negative of 2 squared times 2. It means that only the 2 can go into the square root. The negative sign is not allowed to, go into the square root. Why do I mention this? Because the x here that we're trying to put into the square root, we actually don't know what the sign of this thing is, right? We have to make sure that it's positive so that we are allowed to put that into the square root by squaring it. Now let's determine what the sign of this 1 over x here, this green circle. We have the condition already from the question that x is going to infinity, right? So we've already had the information that x here is 1 over x is going to negative infinity, so x is less than 0, right? Which means that our 1 over x is less than 0. So we can let this 1 over x go into the square root since it's a negative number. Now what we can do is turn this into positive by placing a negative sign in front of it, because if you multiply negative 1 on both sides of this inequality, you're going to have negative 1 over x greater than 0. So in other words, what we can let into the square root is this negative of 1 over x, not the 1 over x itself. Okay, so I'm gonna rewrite this so that I have the positive expression. Now I place a negative sign here and another negative sign to cancel with this negative sign. So this 1 over x now is written as negative of negative 1 over x. And since we know that negative of 1 over x is greater than 0, so we can let this negative 1 over x, this green box, go into the square root by squaring it. So we have x goes to infinity, negative infinity, negative of this square root, negative 1 over x, bracket square, times 2x squared minus 5x plus 3. Divided by 1 minus 7 over x. And now we simplify the top to negative of this 1 over x squared times 2x squared minus 5x plus 3 divided by this, which is negative of 2 minus 5 over x plus 3 over x squared divided by this. And now we have these terms going to 0 because x is in the denominator, and we know that x is going to infinity, so the denominator is getting infinitely large, so the fraction is gonna be very, very small, and it approaches 0. So these things, they all go to 0. And now we are left with only the square root of 2 on the top and 1 in the bottom. So the answer is negative square root of 2 divided by 1, which is negative square root of 2. Okay, so that is how we handle this question. And the difficult stuff here is handling the negative sign of that expression. When we want to let something go into the square root, we have to make sure that that thing is positive. When that thing is not positive, you have to kind of rewrite the expression so that you left the you leave the negative sign in outside of the square root. Okay, so that is how we do this question.